Okay, so we can start by looking at the first exercise of the text. The text was given in last year in February, and so the first exercise is about packet transmission. There is a network with a simple topology, and we have a set of hosts. A, B, C, D, and D, and 3 routers, R1, R2, and 3. And these hosts are producing packets, as specified in the text, with different destinations. And in particular, host A is starting to produce packets at time t equal to 0, and it produces the set of packets that you see there. One for E, 2 for B, 1 for D, and another one for B, one after the other. And then also host D starts sending a sequence of 2 packets going to host destination C. Can you see? Okay. And then we have this topology. As you can see, it's very simple, so there is no problem of routing. Each source is connected to destination with just one and just one path, and then you have everything specified in terms of capacity of the links and the distance. And here the text says that we have to consider coaxial cables and therefore guided waves. So the delay per unit of length, as you know, is 5 microseconds per kilometer. This data sometimes is not given, and you should remember it. This time it was given. So first of all, we can start calculating all the features of the network provided by the physical layer. And in particular, we can calculate the delays and the transmission times. The propagation delay, as you know, is given by the propagation delay per unit of length multiplied by the distance given in kilometers. Here numbers are very simple. So we can, for instance, if you take the link number 1, we have tau D1, which is 4 kilometers, and therefore the delay is immediately given by 4 times 5 microseconds, okay, which is 20 microseconds. And then we have the delay on link 2, which is 10 microseconds. Propagation delay on link 3 is 30 microseconds. Propagation delay on link 4 is again 10 microseconds. Then we have link 5, which is 0 microsecond. Link 5, as you can see, has a distance that can be approximated with 0. It's very short. And then we have link 6. 6 is 0 again. Link 6 is this one. And finally, link 7, which is 30 microseconds. Okay. Now we can do a similar calculation for the transmission times. This is clearly a problem that regards transmission of packets, and you have to follow each packet link by link from the source to the destination. So we need to calculate the transmission time at each transmission interface, and all the links are symmetrical, so the number of the link stands for transmission in both directions. Okay, and as you know, the transmission time is given by the length of the packet divided by the capacity of the link. What about the length of the packet? Here we can see that all the packets have an equal length and comprises a header of 2 bytes and a payload of 28 bytes. Okay, so the total length of the packet is given by the header plus the payload, okay, which is 28 plus 2 bytes, 30 bytes. But you know that all the transmission capacities are given in a bit per second, so we need to transform this in a bit, which is 240 bit. Okay. So when we consider all the links, okay, we have time 1. I am copying it because so it's faster, but again calculations are really simple. In case of T1 we have 240 bit divided by 8 megabit per second, so it's 240 divided by 8 microseconds. Please always remember to put unity of measurements beside the numbers, otherwise the numbers are completely meaningful. Okay, so meaningless, sorry. So this is 30 microseconds. Then we have T2, it's 20 microseconds, and then we have T3, 20 microseconds, T4, 60 microseconds, T5, 60 microseconds as well, T6, 80, T7, 10 microseconds. Okay, and this is just a preliminary calculation. So now we have to work with the time diagrams basically, and here there is another important assumption that is all the nodes operate in the store and forward mode. It means that before retransmitting a packet, we have to receive it completely from the input interface. So now we'll try to use the squares, and in fact this is why in the text we provide also a printed page with small squares. So this is a first axis, then we can write the second one here, third one here. Okay. So we can decide that one small square in this graph represents 10 microseconds. okay, because you can notice that all the parameters we have calculated are multiple of 10 microseconds, so this is the most convenient. And then we can start drawing the packets. Here we have a complexity in terms of the time diagram, because you can see that some packets take a specific route. For instance, packets that are going from A to B are going through R1 and R2 and then R3 and then B. And there is a packet that is going, for instance, to E, which will travel through A, R1, R2 and E. And so we have to differentiate things. And moreover, there are also two packets that are generated in D at a different time, and are going to E. Okay, so it's not quite E, are going to C. So, however, we have to do this representation in a careful way, because it may happen that we have queuing delays in the intermediate nodes. Okay. So let's start from the output interface of A, and A is connected to R1 through the link number 1. Okay. So we can also write here 1 in parentheses. And then we have to fix the instant t equal to 0, which can be this one. Okay. Now the packets that are going out, the packets that are generated in A are the first one to be generated, because they are generated starting from time t equal to 0. And so we can immediately represent them, and the sequence of packets A, B, B, D, and B are going to are generated one after the other. Transmission time here is 30 microseconds, so I can start drawing the packets, and the sequence is E, B1, B2, then we have D, then we have another packet for B3. So if you write the destinations of the packet on the packets, it's easier to identify them. Then they are propagating on link number 1, so there is a propagation delay of 20 microseconds. So they will arrive in R1 after a propagation delay of 20 microseconds. I can maybe write this number here, so that we know that from A to R1 we are crossing link number 1. So this is the propagation delay, and then we are arriving to find all the packets in R1. Okay. Now, packets that are arriving in R1 are going to different destinations, and so they will be, are all going to R2, okay, and they are going to R2 through link number 2. So actually here there is no difference. This is link number 2. They are transmitted after they have been completely received, and immediately after they have been completely received. The transmission time on link number 2 is 20 microseconds. since the duration of the packets received from the source A was 30 microseconds, we don't have any queuing delay in this interface. Okay? So I can start writing before the packets here. Okay, A, B1, B2, D, and B3. They will arrive in R2 after a propagation delay of 10 microseconds. Okay. Now, what happens in R2? In R2, here we have different output ports according to the destinations. So all the packets that are going to B will go through towards R3, crossing this link number 4. Then there is the packet that is going to E, that is going out of this on this link, and the packet is going to D, that is taking another route. So here we can start showing what happens to the packet that is going, for instance, to E, which is the first one. So I can draw another line here. Maybe we can use also different colors. So this packet that is going to E, can paint it in black. Now in R2, we are going towards E through link number 3. No, number 5, sorry. And the transmission time is 80 microseconds. So the first packet that is here will be transmitted in a time it is like that. Okay. The transmission takes a lot, but it doesn't make any problem for the other packets, because the other packets are going to a different destination, so they are queued on a different output queues. Okay. So this packet in E will reach the final destination, and on this link number 5 we have no propagation delay. So this is the end of the propagation for the packet number, packet destined to E, and we can calculate the total propagation time. In order to calculate the total propagation time, we have to sum all the segments. So we can start from this final point here. We don't have any propagation delay on the final link, so it's a 0. Then we have 80 microseconds here, so 8 rectangles, 8 squares. Then we have a propagation delay of 1 microsecond. Then a transmission time of 10 microseconds, 20 microseconds, propagation delay of 20 microseconds again, and finally the transmission time, the initial transmission time, that was 30 microseconds. I multiply everything times 10 so that it's easier to write. And if I am not wrong, you can check later, the final result is 140 microseconds. Okay. So now we have to go to the other packets. We can immediately write what happens to the packet that is going to D, because the packet that is going to D is not again, it takes another output port, so it's not influenced by the other packets. I can, for instance, use the red. So here we can now draw another line, and this is representing the final destination D. Okay. Now from R2 to D, so on this transmission, we are crossing link number 6. Okay. And the transmission starts in the moment that R2 has received completely the packet for D. On transmission on link number 6, the transmission takes no, I made a mistake. On link number 6, the transmission takes 80 microseconds. Okay. And on link number 6, we have no. On link number, sorry, this is not link number 6, but it's link, unfortunately, is link number 3. Okay. It's link number 3. On link number 3, the transmission time is 20 microseconds. This is D. And the propagation delay is 30 microseconds. So D is transmitted here, and it will be received in D in this moment. Okay. Instead, I made a mistake on the transmission time of E, because this is link number, it's going to E on link number 5 and not number 6, so the transmission time is 60 microseconds. Okay. Instead, if we consider link the packet that is arriving in the D, actually D is the final destination. This is not here. Okay. No. Ah. Made a mistake again. So D is connected through link number 3. It was corrected as before.